Just say it, man. Don't make me ask 20 questions.
What is the point?
Get to the point.
Just say it already!
Welcome to the Podcram. For our third episode, we have Neil Gershenfeld on the Lex Friedman Podcast number 380. As of 2024, this is still my favorite episode of any podcast I've heard, and I highly recommend that anyone who gets excited about the ideas mentioned here, go listen to the full thing. I certainly will again.
You have spent your life working at the boundary between bits and atoms, so the digital and the physical. What have you learned about engineering and about nature reality from working at this divide, trying to bridge this divide?
I never understood the difference between computer science and physical science. But Turing's machine, that's the foundation of modern computing, has a simple physics mistake, which is the head is distinct from the tape. So in the Turing machine, there's a head that programmatically moves and reads and writes a tape. The head is distinct from the tape, which means persistence of information is separate from interaction with information. So the legacy of that is the computer somebody's using to watch this is spending much of its effort moving information from storage transistors to processing transistors, even though they have the same computational complexity. So in computer science, when you learn about computing, there's a ridiculous taxonomy of about 100 different models of computation, but they're all fictions. In physics, a patch of space occupies space. It stores state. It takes time to transit, and you can interact. That is the only model of computation that's physical. Everything else is a fiction. If you're familiar with the movie The Metropolis, people would frolic upstairs in the gardens, and down in the basement, people would move levers.
Yes.
And that's how computing exists today, that we pretend software is not physical. It's separate from hardware. And the whole canon of computer science is based on this fiction that bits aren't constrained by atoms, but all sorts of scaling issues in computing come from that boundary, but all sorts of opportunities come from that boundary. And so you can trace it all the way back to Turing's machine making this mistake between the head and the tape. Turing and von Neumann both knew this. So all of the canon of computer scientists credits them for what was never meant to be a computer architecture. Both Turing and von Neumann ended their life studying exactly how software becomes hardware. So von Neumann studied self-reproducing automata, how a machine communicates its own construction. Turing studied morphogenesis, how genes give rise to form. They ended their life studying the embodiment of computation, something that's been forgotten by the canon of computing, but developed sort of off to the sides by a really interesting lineage.
So there's no distinction between the head and the tape, between the computer and the computation. It is all computation.
It's really just a core thought over and over again, just very literally how bits and atoms relate, just going from digital to physical in many different domains. Claude Shannon at MIT wrote the best master's thesis ever. In his master's thesis, he invented our modern notion of digital logic. The real birth of computerized digital manufacturing is 4 billion years ago. That's the evolutionary age of the ribosome. So the way you're manufactured is there's a code that describes you, the genetic code. It goes to a micro machine, the ribosome, which is this molecular factory that builds the molecules that are you. In our genome, what are called Hox genes, and these are morphogenes. And nowhere in your genome is the number 5. It doesn't store the fact that you have 5 fingers. What it stores is what's called a developmental program. It's a series of steps, and the steps have the character of like grow up a gradient or break symmetry. And at the end of that developmental program, you have 5 fingers. So you are stored not as a body plan, but as a growth plan. And there's 2 reasons for that. One reason is just compression. Billions of genes can place trillions of cells. But the much deeper one is evolution doesn't randomly perturb. Almost anything you did randomly in the genome would be fatal or inconsequential, but not interesting.
Mm-hmm.
But when you modify things in these developmental programs, you go from like webs for swimming to fingers, or you go from walking to wings for flying. It's a space in which search is interesting. The key thing to know about that is there are about 20 amino acids that get assembled. Mm-hmm. And in that machinery, it does everything Shannon and von Neumann taught us. You detect and correct errors. So if you mix chemicals, the error rate is about a part in 100. When you elongate a protein in the ribosome, it's about a part in 10 to the 4. When you replicate DNA, there's an extra level of error correction. It's a part in 10 to the 8. And so in the molecules that make you can detect and correct errors, and you don't need a ruler to make you. The geometry comes from your parts. So now compare a child playing with Lego and a state-of-the-art 3D printer or computerized milling machine. The tower made by a child is more accurate than their motor control because the act of snapping the bricks together gives you a constraint on the joints. You can join bricks made out of dissimilar materials. You don't need a ruler for Lego because the geometry locally gives you the global parts. And there's no Lego trash. The parts have enough information to disassemble them. Those are exactly the properties of a digital code.
The unreliable is made reliable.
Yes, absolutely. So what the ribosome figured out 4 billion years ago is how to embody these digital properties, but not for communication or computation in effect, but for construction. So a number of projects in my lab have been studying the idea of digital materials. And think of a digital material just as Lego bricks. The precise meaning is a discrete set of parts reversibly joined with global geometry determined from local constraints. The ribosome can make an elephant one molecule at a time. Ribosomes are slow. They run at about one molecule a second, but ribosomes make ribosomes. So you have trillions of them, and that makes an elephant. In the same way, these little assembly robots I'm describing can make giant structures at heart because this robot can be made out of the parts it's making. So the robots can make the robots, so you build up the capacity of robotic assembly. So how do you give birth to a thing that knows how to make itself? And so with Stan Ulam, he invented cellular automata as a way to simulate these, but that was theoretical. Now the work I'm describing in my lab is fundamentally how to realize it, how to realize self-reproducing automata. And so, this is something von Neumann thought very deeply and very beautifully about theoretically. And it's right at this intersection. It's not communication or computation or fabrication. It's right at this intersection where communication and computation meets fabrication. Now, the reason self-reproducing automata intellectually is so important because this is the foundation of life. This is really just understanding the essence of life. And in effect, we're trying to create life in non-living material. The reason it's so important technologically is because that's how you scale capacity. That's how you can make an elephant from a ribosome because the assemblers make assemblers. Now, let me give you the numbers. Right now, we're living in AI mania explosion time. Let me relate that to what we're talking about. 100 petaflop computer, which is a current generation supercomputer, not quite the biggest ones, does 10 to the 17 ops per second. Your brain does 10 to the 17 ops per second. It has about 10 to the 15 synapses, and they run at about 100 hertz. The supercomputer has about 10 to the 15 transistors in the processors, 10 to the 15 transistors in the memory, which is the synapses in your brain. So you could view AI as a breakthrough, but the real breakthrough was, as of a year or two ago, the performance of the computers matched the computational capacity of a brain. So we'd be sort of derelict if they couldn't do about the same thing. But now the reason I'm mentioning that is the chip fab making the supercomputer is placing about 10 to the 10 transistors a second. While you're digesting your lunch right now, you're placing about 10 to the 18 parts per second. So in computational capacity, it's done. We've caught up. But there's 8 orders of magnitude difference in the rate at which biology can build versus state-of-the-art manufacturing can build. And that distinction is what we're talking about. Now, what's interesting is if you want to buy electronics today from a vendor, there are hundreds of thousands of types of resistors or capacitors or transistors, huge inventory. All of biology is just made from this inventory of 20 parts, the amino acids. And by composing them, you can create all of life. And so as part of this digitization of materials, we're in effect trying to create something like amino acids for engineering, creating all of technology from 20 parts. There's a wonderful series of books by Gingery. Book 1 is how to make a charcoal furnace. And at the end of book 7, you have a machine shop. So it's sort of how you do your own personal industrial revolution. ISRU is what NASA calls in situ resource utilization. And that's how do you go to a planet and create a civilization. ISRU has essentially assumed Gingery. You go through the Industrial Revolution and you create the inventory of 100,000 resistors. What we're finding is the minimum building blocks for a civilization is roughly 20 parts. So what's interesting about the amino acids is they're not interesting. They're hydrophobic or hydrophilic, basic or acidic. They have typical but not extremal properties, but they're good enough you can combine them to make you. In biology, primary structure is the code in the messenger RNA that says what the ribosome should build.
Yeah.
Secondary structure are geometrical motifs. They're things like helices or sheets. Tertiary structures are functional elements like electron donors or acceptors. Quaternary structure is things like molecular motors that are moving my mouth or making the synapses work in my brain. Go through primary, secondary, tertiary, quaternary. Yeah. You extract properties like conducting, insulating, semiconducting, magnetic, dielectric, flexural. These are the kind of, roughly 20 properties. Those are enough for us to assemble logic, and they're enough for us to assemble actuation. With logic and actuation, we can make micro robots. The micro robots can build bigger robots. The bigger robots can then take the building block materials and make the structural elements that you then do to make construction. And then you boot up through the stages of a technological civilization. What this is leading towards is technology doesn't need enormous global supply chains. It just needs about 20 properties you can compose to create all technology as the minimum building blocks for a technological civilization. I like thinking about how you bootstrap a civilization on Mars, that problem, because it has really profound implications back here on Earth about how we live sustainably. Trash is an analog concept.
Yeah.
There's no trash in a forest. All the parts get disassembled and reused. Trash means something doesn't have enough information to tell you how to reuse it.
Yeah.
It's as simple as there's no trash in a Lego room. When you assemble Lego, the Lego bricks have enough information to disassemble them. There are all sorts of limitations on 3D printing to the kinds of materials you can print, the kind of functionality you can print. We're just not going to get to making everything in a cell phone on a single printer. But I do expect to make everything in a cell phone with an assembler. And so instead of printing and cutting technologically, it's this transition to assembling and disassembling. Going back to Shannon and von Neumann, going back to the ribosome 4 billion years ago. 3D printers are useful, but in a fab lab, it's one of maybe 10 machines. It's used, but it's only part of the machines. The real technological change is when we go from printing and cutting to assembling and disassembling. That reduces inventories of hundreds of thousands of parts to just having a few parts to make almost anything. It reduces global supply chains to locally sourcing these building blocks. But one of the key implications is it gets rid of technological trash because you can disassemble and reuse the parts, not throw them away. And so initially that's of interest for things at the end of long supply chains, like satellites on orbit. But one of the things coming is eliminating technical trash through reuse of the building blocks. And so it's digitizing the materials. The precise meaning is a discrete set of parts reversibly joined with global geometry determined from local constraints.
Thanks for listening to this installment of The Podgram. I hope it contains something useful for you. If you enjoy these selections and are curious about the curator's own thoughts, you can check out my other podcast, Psychic Lube, where I share concise concepts meant to grease the intellectual gears and help get your creative juices flowing. Each episode is an ongoing collaborative project that welcomes listeners to expand or rebut its points by email or comment, the most interesting of which get incorporated through periodic re-recordings. As always, if you're intrigued by today's content, I encourage you to go listen to the full podcast in its original form directly from its creators so that their sponsors keep paying them to make stuff for us and nobody feels compelled to sue me for copyright infringement. Now, get off your phone and go do smart stuff. Have a productive day.